Hello and welcome to Calc Lesson number 46. Today we're actually going to do two things. We are first going to explore the vertical motion model, and then we will do a quick exploration into area under the curve. So I know you've already done a ton of practice with basic integration, but let's just do a quick review or a quick warm-up before we jump into our application. So here we want to take the integral of 2x cubed minus 6x squared plus x dx. When we do that, remember our 2 is that constant, it stays. X goes to the 1 higher power over 3 plus 1. Minus, we can take each integral, so our 6 is going to stay. X to the 1 higher power over 2 plus 1. There's a 1 here, so we just leave that 1. X to the 1 plus 1 over 1 plus 1. As we simplify, this becomes 2 over 4 x to the 4th minus 6 over 3 x to the 3rd plus 1/2 x squared. And let's just go ahead and simplify those fractions. 2 over 4 is 1/2 x to the 4th minus 6 over 3 is 2x cubed plus 1/2 x squared. And because this is an indefinite integral, we need to add that plus c at the end there. Okay, so let's actually jump into using that integral for our vertical motion model. So let's start by recalling the vertical motion model, which we've used earlier this year. S of t is equal to negative 16t squared plus v sub 0 times t, where v sub 0 here is our initial velocity, plus s sub 0, where s sub 0 is your initial position, which works when you have that gravitational force. In the first half of the year, we learned that s of t would be our position, and then the derivative s prime of t would be equal to the velocity, and then the derivative of the velocity, or the second derivative of the position, would be equal to acceleration. That was back when we were doing differentiation. Now that we can actually take the integral, we can go ahead and work backwards, or we can work in reverse. Okay, so let's just work our way through an example. This says a ball is thrown up with an initial velocity of 64 feet per second from an initial height of 80 feet. We want to find the position function that relates the object's height s as a function of time t. So let's just note what we're looking for here is the position function s of t. And what they tell us originally is that we have our ball is being thrown up with an initial velocity of 64 feet per second from an initial height of 80 feet. So for number 1, let's go ahead and fill in s of 0. So s is our position function. So at time 0, that would be our initial position or our initial height. So our initial height was that 80 feet. S prime of 0, S prime of t, remember, is just our velocity function. S prime of 0 would be the initial velocity, which they told us was that 64 feet per second. S double prime of t, the second derivative of the position, remember, is the derivative of velocity or is equal to acceleration. And because there's no acceleration mentioned here, the only acceleration we need to worry about is gravity, which remember has a pull of negative 32 feet per second, negative because it's pulling you down. So what we want to do now is find our general solutions. This is a word that we looked at in that first lesson, the general solution. S prime of t would be the integral of s double prime. So we want to take the function that we wrote, s prime of t here, negative 32. Sorry, s double prime of t we said was negative 32. So we want to take the integral of negative 32 dt. Using the power rules on our formula sheet, this would just become negative 32 t to the first power over 1. So just negative 32t. And because this is the general solution, we're going to add that plus c. So that would be our s prime of t equation. Okay, so in red we have the information that we already found, s of 0, s prime of 0, and then our general solution, s prime of t, is equal to negative 32t plus c. For number 4, what we're interested in doing is actually finding the particular solution, which means we need to solve for c. So let's choose a value that we know about s prime. So the only value we've really indicated so far about s prime is that s prime of 0 equals 64. So let's go ahead and take our s prime of t equation and let's plug in the point 0, 64 to solve for t. So if we look at s prime of t is that negative 32t plus c, and let's use the fact that s prime of 0 equals 64. Then what we have, is that 64 equals negative 32 times 0 plus c, which gives us that 64, this goes away, is just equal to c. So our particular solution, s prime of t, given that we have the point 064, is negative 32t plus 64. So we can actually go ahead and fill in our c value there. So far we took the information that we were given about this ball being thrown up. We only had the initial velocity, the initial position. We used those two givens to help us find our particular solution for s prime of t, which remember is the same as our velocity. And now we want to find the general solution. So we're going back to our general solution, integrating s prime of t to find our position function, s of t. So here this means we want to integrate negative 32t plus 64 dt. So again, using our power rule, we keep our negative, I'm going to come down here, we keep our negative 32 t to the 1 plus 1 over 1 plus 1 plus 64t to the 0 plus 1 over 1. Let's simplify, so this becomes s of t equals negative 32 over 2 is just negative 16t squared plus 64t, and because this is a general solution, plus c. So now we took it a step further. We took s prime and integrated to find the general solution for our position function. So again, everything we found is already written in red. For number 6, we want to once again use one of the values that we knew at the beginning, a value that we know, this time about s of t, to find the particular solution to our position function. So again, the only information we were given about our position was the initial position. So we want to take our general solution, s of t, equals negative 16t squared plus 64t plus c, and use the given information that our initial position was 80 feet, and go ahead and plug that in to solve for c. So we have 80 equals negative 16 times 0 squared plus 64 times 0 plus c. These all go away, so we're left with 80 equals c, which means our particular solution, s of t, our position function that we were looking for, is equal to negative 16t squared plus 64t plus 80. And now we can use all of that to actually answer a question about the ball's position. So for number 7, this says, when does the ball hit the ground? Which really means, when does our position, s of t, equal 0? So let's go ahead and set our position function equal to 0, negative 16t squared plus 64t plus 80 equals 0. Let's go ahead and factor out a negative 16. So we have t squared minus 4t minus 5 equals 0, which we can factor. So this becomes negative 16. Factors of negative 5 that add up to negative 4 would be t minus 5 and t plus 1, which gives us t equals 5 and t equals negative 1. We know we can't have that negative time, so t equals 5 will be our solution. So the ball hits the ground at t equals 5 seconds. So just as a recap, we were only given information about our initial velocity and our initial height. We were able to go all the way backwards from using only the fact that we knew gravity was pulling our ball down to go all the way back to finding our position equation and then answering a question about when the ball hits the ground. Okay, homework 46 is listed here. It's a practice mixed of your basic integration that you learned in the last lesson and then reviewed today, and then also the vertical motion model. So depending on what your teacher says, you might pause the video here and then do the next part later, or you might continue watching now, but here is your homework 46 assignment. So we're going to transition to a quick exploration into area under the curve. During this exploration, you will be asked to pause the video, try something on your own, and then come back and check what you did or check how you did it. For this, there is a handout that your teacher might have given to you, or you might just want to grab a piece of paper and a pencil so you have a place to put your work. So the first thing you want to do is look at the graph here. You have the function y equals 2x. Then you have a shaded region underneath that curve. Go ahead and pause the video and try to find the area of that shaded region. Here's a hint. You might want to use geometric formulas that you've learned in the past. Hopefully you recognize the shaded region as being a right triangle, and the area formula for a right triangle is 1/2 the base times the height. All you had to do was identify the length of the base and the length of the height in order to plug in. Using this point where your line 2x intersects with the line x equals 4, you find the point 4, 8, given the equation y equals 2x, which gave you your base as 4 and your height as 8. Plugging into your area equation, you should get your area of the shaded region as 16 units squared. So the next one we want to try is similar. Here we have a shaded region where it's actually a region that's bounded by the axes and then also the line x equals 1 and then the line y equals 1 plus 3x. So again, go ahead and pause the video to try to find the area of this shaded region. Here's a hint. You might want to break this into two shapes that you already know in order to find your area. So if you followed the hints, you hopefully found the area of the red rectangle to be 1 unit squared using that point 1, 1. And then to find the area of the green right triangle, again, you needed that 1/2 base times height. Just be careful when you identify the height. Notice that even though the point is at 1, 4, the height is only 3 because you have to account for this 1 down at the bottom. And then when you combine both areas and you add them together, you get 1 plus 3/2, which is just equal to 5/2 units squared. Now for this next one, the directions are a little bit different. Here we want to find just the approximate area, which means we're not going to be able to find exactly the area like we were in numbers 1 and 2. So just like before, there's a hint. Try to break it into shapes that you can easily find the area of, even if they don't fit perfectly over your shaded region. So go ahead and pause the video, see if you can come up with a good way to find the area as close as you can of the shaded region. So there were a couple of different ways that you could have done this. So maybe you broke this area into 3 rectangles and you found the rectangle by identifying the right-hand endpoint. If you were to do that, you would have added all 3 of the areas of these rectangles up. So for the first one, you would have done your length times your width. So the width is going to be 1 and the height here is going to go up to 2. So that would be your 1 times 2. Your second rectangle, your width is still 1, but this time it goes all the way up to 5. So that would be your 1 times 5. And then your third rectangle, whoops, my computer's a little laggy. Your width is still that 1, but this time it goes all the way up to that point 10. That would be your 1 times 10. And when you add all of those up, you get your area as 17 units squared. Now, obviously, looking at the red shaded part versus what was originally shaded, we would call this an overestimation. Okay, so like I said, that wasn't the only way you could have done it. Maybe you saw 3 rectangles as well, but instead of using the right endpoint, you use the left endpoint in order to create your rectangle. So you would use the point 0, 1, 1, 2, and 2, 5. As you were doing that, then when you found the area of your first rectangle, length times width would be 1 times 1. Your second rectangle, length times width would be 1 times 2. And then your third rectangle still has that width of 1, but this time goes up to 5. So that would be your 1 times 5. So your area here would be 1 plus 2 plus 5, or 8 units squared. Now that is a very different answer than what we had gotten when we did the right endpoint. And obviously, as you can see in the picture, the green highlighted does not quite cover the complete shaded region. So we would call this an underestimation. Now maybe you took it a step further and you saw that both sets of rectangles I just showed you gave us an approximate area, but both were pretty off. We either saw an over or an underestimation. Maybe you decided to break this into trapezoids using both endpoints. So maybe you remember the area for a trapezoid is 1/2 base 1 plus base 2 times the height. So looking at each of these, the height is actually going to be that distance on the x-axis. So for the first one, it would be 1/2 base 1 times base 2, our first base would be the distance up to 1, and our second base would be the distance up to 2, and our height is that 1. Our second trapezoid in the middle here, 1/2, base 1 is 2, and base 2 is 5, times our height is 1, and then our third trapezoid, 1/2, base 1 is 5, base 2 is 10, times our height is 1. When you add it all together, we get 25 over 2, or 12.5 units squared. Still not an exact, still an approximate area, but maybe a little bit closer than either of the last two that we saw. So after exploring those few options, use your knowledge and what you've learned today to try to find the closest approximation, the closest approximate area of the shaded region here. Write down all of your work and be prepared to justify your answer in a little discussion. So go ahead and pause the video and go ahead and try. Okay, so something important that they gave us here is the equation y equals 4x minus x squared. Using our algebra 2 skills, we can find the vertex of our parabola to be at 2, 4. We can find the zeros of our parabola to be at 0, 0, and at 4, 0. And then we can identify the points 1, 3, and 3, 3 to try to help us set up this, get started on this area. From there, I'm going to break this into familiar shapes. That's my method for now. So I'm going to start by breaking this into a rectangle right in the middle here. And I know that that rectangle is equal to sorry, my computer is lagging. Length times width. My length here between 1 and 3 would be 2, or my width, and my height or my length would go all the way up to 4. So the area of that rectangle would be equal to 8. Then I also see that I have a pretty close to a right triangle on the side here, and pretty close to a right triangle on the side here. The area for each of those would be 1/2 the base times the height, where my base is 1 and my height is 3. So that puts me at 3/2, and I have 2 of them. So my total area, or my total approximate area, the way I found it, would be 8 plus 3, or 11 units squared. So maybe you did it a different way than me. That would be how I would find the approximation. Now we want to find the closest ones. You can go ahead and compare with your pals around you, and the actual exact area under this curve should be 10 2/3 units squared. So go ahead and check with your friends, see if anyone got closer than you, see if anyone got closer than me. But your exact area should be 10 2/3 units squared. So what was the major difference between the first two and the last two problems? Hopefully you think that in the first two we had those linear equations that made it easy for us to create shapes like rectangles and triangles, things that we know the exact area of, whereas in numbers 3 and 4 we had those curved equations, those parabolas, that made it more difficult to find exact shapes that fit in, and we had to kind of find ways to approximate. So this is going to help us lead into what we're going to be studying over the next couple of lessons. So we were talking about the tangent line problem for a lot of this year, where we were using limits to find slopes of tangent lines. Now we're going to transition into another famous calculus problem called the area problem, where we are once again going to be using limits with areas of rectangles to find the area under a curve. So we're still going to be applying our calculus concepts, this time just to a different type of problem. And stay tuned over the next couple of lessons to see how exactly we can do that. Overall, really fantastic job with this area exploration. If you have any questions, you can go ahead and ask your teacher. And don't forget about homework 46, which is posted in the middle of this video and is likely posted for you wherever your teacher usually posts your homework.